Hi there, and welcome to another Pencast for the course Reasoning and Logic. In this one, we treat an old exam question that's about an odd definition of what prime numbers might be. A number is prime, or it has the property p, if for all numbers larger than 4, that number does not divide it. Now the question already tells us that this description is incorrect, and that we should give an example of a number that has the property, even though it is not prime, and we should give an example of a number that does not have the property, even though it is prime. So let's start with the second one, a prime that does not have the property p. Well, what happens if we take n equal to x? Then n divides x, right? Because any number divides itself. Well, perhaps with the exception of 0. So, for any number larger than 4, there is going to be a counterexample to this for all statement. For the number n equals x, it is not going to hold. So there is always a divisor for n larger than 4. So for a prime that does not have the property p, just pick any prime larger than 4. For instance, we could take x equals 17, which is a prime larger than 4. And if we take a look, it is not true that for all n doesn't divide x, because take n equals 17. For n equals 17, n will divide x. Now how about the other one, a non-prime that has the property p? We'll take a look at what happens when x is smaller than 4. When x is smaller than 4, then, well, surely no n larger than 4 will divide it. In other words, the for all statement is going to be true, and it's going to have the property p. So take a non-prime number smaller than or equal to 4. For instance, x equals 4, but x equals 1 would also have done. If we take x equals 4, then, well, any number larger than 4 isn't going to divide it. 5 is not a divisor of 4, neither is 6, nor is 7, nor is any number larger than 4. The only divisors it has are 1, 2, and 4, which are all smaller or equal to 4. Which means that 4, although it's not a prime, does have the property p. And so x equals 4 and x equals 17 can be two counterexamples to this definition of prime numbers. So that's how I would tackle the problem. Hopefully you can do something similar in the future now. And with that, we've come to the end of this Pencast. See you around for the next one.